Solubility rules. The rules that you use to predict whether something will be soluble or not in a given solvent. The rules for ionic and covalent compounds are different when talking about solubility. So we're going to focus on the solubility rules for covalent compound first, then we'll talk about the solubility rules for ionic compound. To dissolve some particles in a solvent is like to put a person in a group of strangers. Let's think about this. If you are put into a group of strangers, how do you know if you will be accepted or if you will be soluble in that group? Well, you only know that through communication. Okay, for those group of people, they see a stranger comes, they will start to interact with you. Some of them may talk to you, you respond, okay? Depending on how your communication goes, words can spread. Okay, there may be a few of those people interact with you really well, then they pass the words to some other friends. They tell them, you know what? This newcomer is very nice, very funny, and nice personality. We have common interests, we have common languages. Then you are accepted, you are dissolved in that group of people. Well, how do particles communicate? When a particle is in a solvent, how do we know those particles will be accepted by the solvent or not? Well, through interactions between the solvent and the solute particles. Particles interact with each other through intermolecular forces. So there are three kinds of intermolecular forces. London forces, okay, dipole-dipole, and hydrogen bonds. These are like three different languages molecules can speak. London forces is the only language for nonpolar molecules. Nonpolar molecules can only speak London forces. They can only interact with each other by London forces. Dipole-dipole is for polar molecules. Polar molecules. Well, polar molecules also have London force. However, we clarified that earlier because dipole-dipole is way stronger than London force. London force is not significant for polar molecules. While hydrogen bonds is the language preferred for the unique kinds of molecules, molecules with hydrogen connected with NOF. Okay. All right. So if the solid particles can communicate with the solvent particles with the same kind of language, preferred language, then the solid particles will be accepted by the solvent, which means the greater the difference in solvent and solid polarity, the less soluble. If they differ in polarities, they do not have common languages. Okay? Then it is going to be less soluble for that solid. Substances of like polarities tend to be more soluble in each other than substances that differ in polarity. When they have similar polarities, they have common languages. If the solid and solvent particles are both nonpolar particles, they speak their preferred language, London dispersion. Okay, they like each other. They will be soluble in each other. So nonpolar will be soluble in nonpolar solvents. Polar molecules prefer dipole-dipole interaction. Well, if both of them are polar, then they tend to be soluble in each other. Hydrogen bond is the strongest dipole-dipole interaction, basically. So if both solvent and solid particles can communicate by hydrogen bonding, that solid will be very soluble. All right, so the rule for molecular compounds in regards to the solubility is called like dissolves like. Okay? Like dissolves like is the solubility rule for molecular compounds. The word like means similar in polarity. Okay. Water is a very polar solvent. If you are given a molecule and they ask you, will this molecule be soluble in water or not? What do? You draw the loose structure, predict the polarity. If it is polar, it will be very likely to be soluble in water. If it can form hydrogen bonds with water, then it will be very soluble in water. If they provide you with a molecule like a gasoline is a nonpolar molecule who doesn't speak dipole force, who doesn't speak hydrogen bonds. So gases, oil, will not be soluble in water. We all know that. Oil and water, they don't mix. Why? They cannot communicate. Oil molecules can only speak with each other by London forces. Water prefer hydrogen bonds. That's it. Again, like dissolved like means molecules with similar polarities tend to be soluble in each other. This rule only applies to molecular compounds. What about ionic compounds? If it is ionic compounds, we will use the solubility guidelines for ionic compounds in water, which is on the next slide. All right, this is the table that shows us the guidelines for the solubility of ionic compounds in water. When you do your homework, your quizzes, you want to make sure you have this chart in front of you and predict the solubility. Let's briefly go through some of this to know how to use it. So this table has two sections. The first section are the compounds that are soluble in water. The second section are the insoluble compounds. Now, on the left of each section, they tell you what kinds of compounds will be soluble. On the right, it tells you if there is any exception. So let's see. Group 1A metals, lithium ion, sodium ion, potassium ion. If the ionic compound contains group 1A metal in it, it will be soluble and there's no exception. For example, NaCl, sodium chloride. Sodium chloride has sodium ion in it. Of course, it has chloride ion, but it is not mentioned about chloride. As long as the compound has sodium ion, which is a group 1A metal, the compound will be soluble. There's no exception. Potassium sulfate, soluble because it has potassium ions in it. Make sense? So, group 1A metal, if the positive ion is ammonium ion, if the negative ion is acetate ion, if the negative ion is nitrate ion, they're all soluble. There's no exceptions. Let's talk about an example for this. Nitrate ion, for example, silver nitrate. That is a compound that has nitrate ion in it. If the ionic compound has nitrate ion in it, guaranteed water soluble, no exception. All right, now let's look at the next one. Chloride. Compound with chloride will be soluble. However, there's exceptions. Okay, for example, AgCl, silver chloride. If you look at the chloride, this table tells you, all right, compound with chloride is soluble. However, if you look at the exception, if the positive ion is silver ion, it is an exception. then it is insoluble. So silver chloride is insoluble. Make sense to you? Lead 2 chloride. Well, the negative ion is chloride. It looks like it's going to be soluble. However, lead 2 plus is an exception. As a result, lead 2 chloride is insoluble. Make sense to you? All right, iron 3 chloride. Iron 3 chloride, the negative ion is chloride. It should be soluble. Look at the exception. Iron 3 plus is not the exception. Therefore, iron 3 chloride is soluble. So far, so good. All right, let's move down to the next section. Compounds that are not soluble. Carbonate ion. If a compound has carbonate ion, it will be insoluble unless the positive ion is group 1A metals or ammonium. For example, okay, calcium carbonate. The negative ion is carbonate ion. Calcium ion is not one of those. Calcium ion is not one of these. Therefore, calcium carbonate is insoluble. All these compounds in this section is insoluble. So far, so good. All right, let's look at sodium carbonate. Well, if you look at carbonate ion, you may want to claim, oh, carbonate ion compounds insoluble. However, sodium is group 1A metal, is an exception. So sodium carbonate is soluble. It is actually here as well. Sodium carbonate is one of these compounds. The positive ion is the sodium. So it's soluble. Sulfide. Normally sulfide is insoluble, and here are the exceptions. Well, the exceptions are basically here, but it includes the 2A again. So keep using. It is not very easy to memorize all of this, but if you keep practicing by using this table, gradually you will become very good at this. All right, let's move on to see if we can do some practice on this. Concept check. Which of the following ions will form a compound with lead 2 plus that are generally soluble in water? Okay, which of these will combine? We have A, B, C, D, E. Which of these will combine with lead to form a compound that will be soluble? First of all, E is excluded right away. There's no way E is the answer. Do we understand that? Why? Wait a minute. Sodium ion, we just learned, is going to be soluble. Well, sodium ion is a positive ion. Lead 2 plus is a positive ion. They cannot combine to form a compound. Does that make sense to you? Only A, B, C, D, these negative ions can form a compound with the lead 2 plus. All right, so our job becomes pick the ones from A, B, C, D that can form a compound with the lead 2 plus, and the compound will be soluble in water. All right, let's bring this table here. So lead 2 plus and sulfide. Sulfide is right here. Okay, looks like it is insoluble, but let's check if we have any exception in it. There are exceptions, however, lead 2 plus is not one of those exceptions. So lead 2 plus and sulfide 2 negative will form a compound, and the compound will be insoluble. That is not our answer. Chloride. Lead and chloride is right here. All right, chloride looks like compound with chloride ions should be soluble. Again, let's check the exceptions. Silver plus is an exception. Lead 2 plus is an exception. Oh, all right, lead 2 plus is an exception. Lead 2 plus combined with chloride, the compound will be insoluble. It is not our answer. C, nitrate. Nitrate right here. Nitrate is soluble. Looks like soluble. Let's look at the exception. No exception, none. So lead 2 plus forms a compound with nitrate. It will be soluble. That will be an answer right now. Let's look at D, sulfate. Sulfate is soluble as well, right here. Sulfate is soluble. Let's check the exception. Calcium 2 plus. Lead 2 plus right here. Again, it's an exception. Lead 2 plus will form a compound with sulfate, and the compound will be insoluble. So the answer for this question is C, nitrate ion. That's how you should use this table. Make sense to you? See you next time.